Okay, so this is APSTAT Lesson 3.2a. So we're going to talk about regression lines today. They're straight line relationship between two quantities. And so there's an image of a regression line. The purpose of a regression line is for prediction. We use this for making predictions, sometimes inside of the data, called interpolation, sometimes outside of the data, called extrapolation. And so the form of this is, so we're using a new term here. It says y hat. So y hat it means the predicted y. So when it has a little hat on that, whatever the variable is, you're predicting it. And that's what we do, right? The explanatory variable explains or predicts the response variable, the y variable. So whenever we're using regression, it's a line of prediction. So we always use that symbol over the y variable. So in this case, it'd be y hat equals a plus bx. Remember where we used to say mx plus b? Typically in stats, we start with the y-intercept. We call it a instead of b. And then we call the slope b instead of m. But it's basically still a linear equation there. It's like mx plus b, but we're starting with the y-intercept when we talk about it that way. Okay, here's a bunch of data about Ford F-150 Super Cruise. And so the data shown in the table, it talks about the miles driven and the price. And so, some of the miles driven may be up to about 140,000 miles, maybe as few as 8,000 some miles there. And so what are the different price points or the price in dollars? It looks like the more you drive, maybe the cheaper it would be. Okay. So it says to make a prediction. Well, what if you wanted to predict? What if you only drove 100,000 miles? So what would that price be? And so we can use the prediction line, the line of regression, to make that prediction. So literally all you're doing is where it says miles driven. By the way, this is my preferred notation. Notice they're not using y hat and x there. Y is price. So this equation says the predicted price, because we're using the regression line to predict the price, is 38,257 minus, that's like your y-intercept. That's if you drive 0 miles, the truck would cost $38,257 minus the 0.1629, that's the slope in the context or the rate of change, times the number of miles driven. That's our x variable. So we like to actually put words in there. Notice that it's okay to have in parentheses miles driven. That's a variable, that's x. It's okay to write price, that's y, right? We're just calling them by their proper names because usually with stats, it's not just x and y. They actually have a meaning to them, those numbers. And just like that slope would have a meaning to it. We'll talk about that in a minute, I think. Okay. So to do this, you literally just plug in the number of miles driven. That's called interpolation in the data. And so you're using the other data values to make the line of prediction called the regression line, and we're using that to make the prediction of, we think that truck will cost $21,967. Can we predict the price of an F-150 with 300,000 miles driven? Wow, that'd be a lot of miles. So I've driven a car up to 250,000 miles. That's a lot. 300,000 is a lot. So if you did that, let's make the prediction. Let's just plug it into the formula, see what happens. And we plug it in and we get a really weird answer. It would cost negative $10,000 for this car. Oh, they would give me $10,000. I would love to have a vehicle where they give me $10,000. So that doesn't make sense, right? It's not logical, right? So that's called extrapolation. And we definitely extrapolated too far away from the data. So if you go too far past, you can go a little bit past and be okay. If you look back at that graph there, so it ends out at about 160,000. If you did 160,000, 160,000, 70,000, that would be about right, I think, for this model. I think you'd get a pretty good prediction. But you're going all the way to 300,000. It's just you're extrapolating too far there. So anytime it's dangerous to extrapolate too far away from all the x values that are in the graph. Because oftentimes those predictions are not going to be accurate. It's not going to have any meaning to them. Appear much larger or much smaller, technically much smaller would also be an extrapolation. So usually it's much larger, but it could be. So what is a residual? So these are vertical distance. That's a big key. I need you to think about those as y values, almost like vertical distances. So you see each one of those points has a vertical line. So the data values there are the red dots. The line of prediction is the line. If you take a measurement from each data point, each actual value, vertically to the line of prediction, you see some of these points are below the line of prediction. Those have a negative residual. Some of these points are above. Those have a positive residual. Interestingly, all the residuals, positive and negative, if you add them all up, will always add up to 0 if that's a regression line. So the difference between the actual y value and the value of the y predicted. The formula is this. So it's the actual y value minus the predicted y value. It's important that you remember these are y values. We're subtracting and adding vertically here. So we're talking about the vertical distance there. So you can see if the actual y value is below the line, the red dot is below, you're going to have a smaller number minus a bigger number, so you're going to get a negative residual. If it's above the line, the actual is going to be bigger than the predicted line, and so you're going to get a positive residual in that case. So find the predicted price for a truck that was driven 70,583. So plug it in to find the predicted, and then we plug in that, we get a predicted price of 26,000. Now, I think there actually was one that was sold that had that same mileage, if we can find it on there. So there it is, I see at the top left. So 21,000, that car was driven 70,583. It actually sold for 21,994. Now, we predicted it would sell for 26,000. So if you do the actual price minus the predicted price, you actually get a negative number. So in the context of this problem, the actual price was $4,765 less than the cost we predicted, was predicted by the regression line, with X equals 70,583 miles driven. So that's the idea of that. And you want to talk in context with that. Usually it kind of makes sense if you're talking in context. Interpreting a regression line. So in the regression line, this is A is the y-intercept, B is the slope. And so in this case, let's interpret the slope. So in the slope is going to be the predicted price. Goes down by, so think of that as a fraction. The numerator is negative 0.1629. The denominator is 1. Remember, change in y over change in x is slope. So the y values, which is price, is going down by 0.16 or 16 cents, 16.29 cents. For each additional 1 mile, the denominator is miles in this case, and so it's going down by that. The y-intercept, what is that going to be? So the y-intercept is, in this case, when the x value is 0. So the x value is miles driven. So when we don't drive any miles, we predict the price of the F-150 will be $38,257. And so you just think about that point, that y-intercept in context. It's very important we include the word predicted. Ooh, that's important, or equivalent in your response. Otherwise, it might appear you believe you're talking about actual y values. So both of those, if you look at them, the predicted, see that word predicted, the predicted price, the predicted price. So when we're talking about regression lines, it's always talking about the predicted price or the predicted y value, whatever the y value is. If you want to write down a script, this is the script. For interpreting the slope, for every 1 unit increase in the x variable, whatever that is, our model predicts either an increase or a decrease of blank in the response variable, which again is the y variable. Talk about all that in context. If you want to interpret the y-intercept, when the explanatory or x variable is at 0, again, you're talking in context, our model predicts blank in the y variable or the response variable. So that's just a script if you want to do it. So this is an activity some students do called the Barbie bungee activity. So they make a chain of rubber bands, they connect Barbie to it, and they drop Barbie like a bungee jump. And so you're trying to see where the lowest point is that her head reaches with a certain number of rubber bands, kind of thing. So here's the scatter plot. They did some tests, and they came up with this line, this regression line, a prediction line. And so that it's y hat equals 27.42 plus 7.21. So now I don't like the form of that. So I much prefer, instead of y hat, you should say distance traveled in parentheses with a hat above it with a little hat. So distance traveled, hat, the predicted distance traveled is 27.42 plus 7.21 times x, which really is the number of rubber bands. So I prefer, instead of x, just put in parentheses the number of rubber bands. It'll make more sense. It'll be easier to work with. Don't use X and Y unless you have to. Whoops. So this one, students did not collect data for 7 rubber bands, predict the distance. So now 7 seems like a reasonable, we didn't do that one, but we could definitely plug that into the formula. So you're just going to plug in 7 for X and go with it. A small package of rubber bands comes with 30 rubber bands. Predict the distance Barbie travel if used all 30 rubber bands. Now the graph only goes to 15. It might be accurate, but I don't know. There could be some weird things that happens when you have that many rubber bands. Maybe the Barbie's not heavy enough to actually kind of use the rubber band force. I'm not sure what could happen, but I'd say part C. I'm not as confident about part B because we extrapolated by a lot there. So I don't think that is trustworthy there. We can come up with a number. You say, oh yeah, 243.72 when you plug it in, but 7's within the intervals, 30 is extrapolation. It's way outside the interview, so we are not as confident about that prediction. In fact, it's probably not going to be accurate. Okay, so then this one, find and interpret the residual for the trial with 4 rubber bands. So if you look on the graph, you can see there's 4, it looks like about 50 there. So that's the actual value, but the predicted value, it's hard to tell exactly what that number is, but we could plug in 4 for X there, because that's the number, X is the number of rubber bands driven. So 27.42 times 7.21X. So we get a predicted value of 56.26. I guess they saw that as 52. I wasn't sure what it was. I thought it might be 50. But you take the actual, whatever you think it is, minus the predicted. And so this is going to be, you can see it's definitely below the line. So it's going to be a negative residual. In this case, they came up with negative 4.26. And so the students, in context, the student's measurement for 4 rubber bands was 4.26 less than the length predicted by the regression line with X equals 4 number of rubber bands. Okay, interpret the slope. Again, so in context, the slope is 7.21 divided by 1, but we're going to say, you know, if you go back to that script, and you think, okay, so for every 1 unit increase in X, for every time the number of rubber bands increases by 1, we predict that the Y, in this case, the distance traveled, will increase by 7.21 centimeters, right? So the predicted distance Barbie has traveled goes up 7.21 centimeters for each additional rubber band that is added. Part B, does the value of the y-intercept have meaning in the context? So the y-intercept is when the X value is 0. So when the number of rubber bands is 0, we predict that the Y value will be 27.42, which means that we predict that the distance traveled will be 27.42 centimeters. Ooh, that's weird. So does have a meaning, but it is predicted the distance travels when there are 0 rubber bands. This is Barbie's predicted height. Oh, that's interesting, right? So we think that Barbie will be 27 centimeters. So I guess that's not that much. For some reason, I thought Barbie might be taller than that, but that makes sense, right? So it actually does have a meaning in the context of this problem. So you have to just think about what that meaning is. Okay, that's your lesson for today.